Okay, we can now start discussing about our lecture. Let's open a new page because we have to quickly jump into the properties of the Fourier transform. As we know from the previous discussion of the continuous time Fourier series, the Fourier transform will also require utilization of several properties for solving questions. Fourier transform. This is the continuous time Fourier transform we are talking about. If it is, or when we start discussing the discrete time Fourier transform, the properties will be repeated according to the discrete time case. All right. We may start from a relatively important property, which is differentiation and integration. And integration. From the question of the first midterm, you may realize that most of the questions may require the knowledge of what happens when you differentiate in time domain, what happens to the Fourier transform of it, or when you take the integral, what happens. Those types of questions are of interest. So we have an x of t whose Fourier transform is capital X of j omega, which is, well, the formula is not important here. In fact, the inverse Fourier transform formula is important. When we take the time derivative of x of t, what kind of a Fourier transform will it correspond to? First of all, we can, it's not very difficult to work on it. We can see that this is the time derivative of the inverse Fourier transform of x of j omega. So we can write it as the time derivative of the inverse Fourier transform formula. So what is it? It is 1 over 2 pi integral from minus infinity to infinity x of j omega e to the j omega t d omega. All right? So we take the time derivative of this one. And inside this expression, the only thing that is related to t is e to the j omega t and nothing else. So we take the time derivative operation up until that location. Integration and derivatives can be interchanged. They are linear operators, and the derivative operator can proceed inside the formula until the point where t is encountered. All the other things can be taken out of the derivative parentheses. So I can write it like this, 1 over 2 pi. Is there a question? Is there a question? Okay. So what I'm doing is this. Let me show it to you. d by dt e to the j omega t d omega. So by linearity of the operators of derivative and integral, I can write this. And the time derivative of e to the j omega t is j omega times e to the j omega t. Times j omega times e to the j omega t d omega, like this. And that makes this thing, this portion, to correspond to the Fourier transform of our new term. So this is the Fourier transform of the new term. What term is it? It is this term. So it is the Fourier transform of d by dt x of t. Okay, because everything inside the integral is e to the j omega t d omega with the 1 over 2 pi, and inside the integral we have this. So whatever is multiplying e to the j omega t inside the integral is the Fourier transform by definition of the inverse Fourier transform, which tells us that let me use this one maybe, thicker one, yeah. D by dt x of t's Fourier transform is j omega times x of j omega, which is something that we already know, right? Because we have been using this for the Fourier series, the continuous time Fourier series too. So let's put it in the box. Same is valid for the Fourier transform. A derivative operator in time domain corresponds to multiplication by j omega in the frequency domain, in the Fourier domain. The integration is just the opposite of this fact. So this is the integral of x of t. So from minus infinity to t, x of tau d tau is corresponding to the integral. And the Fourier transform corresponding to this one is obviously 1 over j omega times x of j omega. Okay, just the inverse operation. Instead of multiplying with j omega, we divide by j omega. But except a point which would require the DC value of the Fourier transform or the signal. Because when we take the derivative of, we are trying, let's say that we are trying to take the derivative of this one. Okay, that means we are taking the derivative of this one, the right-hand side too. And when we take the derivative of this right-hand side, I will erase it, but I can show it to you. If I put a constant term here, plus c, which is independent from time, which has no nothing related with x of t, then that constant term, when you take the derivative, will be eliminated. It will be cancelled out. And that plus c essentially exists. In our case, it is a deterministic term, and that is, okay, let me continue with that. The DC value, pi times the DC value at omega is equal to 0. So I indicated with an impulse at omega is equal to 0. Let me put everything into a red box so that it can be isolated from the rest of the equations. So this is the integral formula, and the integral formula is not therefore only 1 over j omega, but another constant term, and that constant term corresponds to the DC value. So you have to know the DC value, but you have to know the whole Fourier transform. You know capital X of j omega. Just put omega is equal to 0. That would correspond to capital X of 0. And you can use it inside the right-hand side expression. Now we can see an example of this thing. We have seen quite a few examples and a question in the first midterm, which required utilization of this. But the new example is more related to non-periodic or aperiodic signals, which is more related to the Fourier transforms. X of t is equal to u of t. And we know that that is the integral of impulse, delta of t. Or you can say that delta of t is the time derivative of u of t. Okay. So how can we find the relation between the Fourier transform of an impulse and the Fourier transform of a unit step function? So let's try to find out the Fourier transform of a unit step function, because we know that the Fourier transform of impulse is equal to 1. Okay, we have seen it in our previous examples. If it is 1, then the Fourier transform of u of t, or x of t, which is equal to u of t, would be equal to 1 over j omega times 1, which is 1 over j omega, plus pi times the Fourier transform of impulse at 0, x of j omega at 0. X of j omega is 1 everywhere, including 0, so it is times 1 times delta omega. Let's write it without the ones, extra ones. It is 1 over j omega plus pi delta omega. Now that's quite an interesting thing, because it's not the only, it's the correct way of putting the Fourier transform. It is 1 over j omega. 1 over j omega, it's not possible to plot, but we can plot the magnitude of it. For instance, we can plot, let's call this x of j omega, where x of t is equal to u of t. When you try to plot it in magnitude, or let's plot the magnitude, it would look like this. Sorry, not like that. Excuse me. That is j omega in magnitude. This is 1 over j omega in magnitude. So it's more like this. With an impulse here whose magnitude is pi. Now an interesting thing happens when we try to take the derivative of this. Let's try to take the derivative of this expression u of t. So x of t this time is equal to delta t, which is the time derivative of u of t. Now what is the Fourier transform from the formula? We know that x of j omega is equal to, quite simply, j omega times the Fourier transform of u of t. What was the Fourier transform? It's there on the screen. It's 1 over j omega plus pi times delta omega. Because you should be worried if I invert the operation, will it come back to the original and required formula? And this thing seems to be j omega times 1 over j omega is 1, which is the good part, but plus there seems to be j omega times pi times delta omega. Now the question you have to ask to yourselves is, what is this j omega times pi times delta omega? It has a value, interestingly, and that value is 0 because of this. J omega is, let's forget about j. It's let's plot the omega function on the omega axis. It's this, okay? And delta omega is this impulse, and I'm multiplying them. So the impulse is non-zero only at omega is equal to 0. When omega is equal to 0, what is omega? Or what is j omega? That is also 0. So it will become 0 times the impulse. And at this point, when they are multiplied, they will give you 0, which will make the whole thing to be equal to 1. For instance, if I don't use delta omega, but if I use, for instance, delta omega minus 1, then it would be j times pi times delta omega minus 1. So it won't be any value anymore. It will correspond to an impulse. But coincidentally, I'm just multiplying the impulse at the point of 0, which would make it 0 times the impulse, which is 0. So that's why we don't have this part anymore, and we get 1, which is correct. We know that the Fourier transform of an impulse is equal to 1. So no big surprise here. All right, that was property number 1. Let's continue with another property now. It is time scaling and frequency scaling. Time scaling and frequency scaling. We know again from Fourier series and from our example that we have seen before, which was the Fourier transform of a rectangular box. When you make something wider in time domain, that wide thing will cause slower oscillations, slower variations, which means lower frequency. So if you make a signal wider in time domain, the signal becomes narrower in frequency domain, corresponding to lower frequencies, because narrow signals or narrow shapes in the Fourier transform domain correspond to low pass signals, and wider shapes contain higher frequencies. So what you do in time domain, you have to invert the operation in the frequency domain. If you are making wider in time domain, it means narrower function in frequency domain, and vice versa. If you make a narrower signal in time domain, that corresponds to higher frequency, therefore the Fourier transform becomes wider. And the relation is like this. Suppose that you have x of t and its Fourier transform is capital X of j omega, then x of a times the t, you are scaling by a. This a could be positive and negative, and it could be less than 1 in magnitude and greater than 1. If it is greater than 1 in magnitude, it means you are making it a narrower signal. If a is less than 1 in magnitude, it means you're making a wider signal. Then its Fourier transform, first of all, there's a scaling factor that scales the magnitude of the Fourier transform. Forget about that for the time being, but it's there, times capital X of j omega divided by a. So I'm multiplying t by a, therefore I'm dividing omega by a. Okay, they go in an inverse proportions. And it's also valid for negative a's as well. The proof is, again, not very difficult. You just write down the formula of the Fourier transform inside the integral, and you substitute this by changing variables. It will correspond to a new Fourier transform, which really corresponds to this. And the proof is, it can be found in the book. It's very straightforward. It's not very complicated, at least. It's quite straightforward. And for the curious one, I strongly recommend that you take a look at the proofs. But I did the proof for the derivative, for example, here. I have derived the derivative and integral formula from here. But if I do it for all of them, then we will be running out of time. So I'm not going to do this one, but it's easy. And I recommend that you work on it. A good example for this one is precisely when a is equal to -1, because it's like already a property. If you flip around x of t by scaling with -1, by scaling the time with -1, it would correspond to 1 over magnitude of -1, which is 1. So we don't have any scale of magnitude. Capital X of j omega divided by -1, which is minus j omega. Capital X of minus j omega. which is telling me that if you flip around the time signal, its Fourier transform is also flipped around. That is happening for all negative scales. The time is folded, flipped, and the Fourier transform is also flipped. Of course, the magnitude here is just 1. Here is an example, another example, which will help me well, am I really going to do that? It's not really an example. It's just another way of putting things. Capital T times x of capital T times t. So I'm not only scaling the time with a capital T, but I'm also multiplying with magnitude of capital T. That would clearly give you capital X of j omega over capital T. I'm giving you this expression in order that, so that you can find the inverse Fourier transform of the time domain scale signal. This is a frequency scale signal. So how do you find the inverse Fourier transform of it? From the not frequency scaled version of it, if you already know it. Just apply this formula. Now the next property, the third, I guess, it's duality. This is nice. It's a nice property. Duality is telling me that if you have a pair, because these pairs will be provided to you in the examinations, there are tables of typical transform pairs. Some signal, for example, the signal is a rectangular box. You know that its Fourier transform is sinc, and the formula will be given to you. You don't have to derive, you won't have to derive the Fourier transform of a rectangular box in the form of a sinc again and again in an examination. It is x of capital X of j omega. So this pair is given. Now, what you do is you take this capital X of j omega and assume that the axis is not omega, but it's a time axis. So your new time signal is a time signal, but it looks like a Fourier transform that you already know. But you make it a time signal, capital X of t, some sort of, you make. So what is the Fourier transform of this new time signal? Since it's a time signal, we take the Fourier transform and we will get something out of it. And that something will be related to the original Fourier transform, 2 pi times. Of course, it will be a Fourier transform, so that will be containing a parameter of omega, so everything will be a function of omega. But it's going to be like this. In some books, it is saying lowercase x of j omega, but essentially it is minus j omega. This is more accurate, but most of the examples that we tend to see are symmetric around the origin, so x of j omega and x of minus j omega would be the same. That is what makes the ambiguity. So it's telling me this: if I take the Fourier transform, I will get something. If I take the Fourier transform of that something again, then I will get the negative of the original signal. This is something that happens in real life physics, and I always like mentioning about this because many of the students just remember the example, and due to a physical thing. J omega, Alican asked me, instead of j omega, can we write simply omega? That's right. Yeah, in many of the, well, actually, j omega is a function of omega. So in the literature, you can find it like that. Instead of j omega, they just write omega. Of course, j is not a parameter. It's the square root of -1. This is just a notation. It means x of j omega means x of omega, okay? So it's the same. You can just use extra resources from the internet who are just saying omega, that's fine. Now, the thing that I want to show you or illustrate you is a physical phenomenon. Let's think of a person, okay? And let's think of a lens, an optical lens. What do we know from optical physics? These rays, these light rays, go into this lens and they merge at the point of the focus, and then they move. So this is the focal length, okay? But at twice the focal length, if you put a curtain or something like that, you will see that you observe this person like this, okay? It is regenerated. Believe it or not, this Fourier thing and this optical thing are related to one another, and it is known as the Fourier optics. And the Fourier optics tells us many things. It is telling us that if you go one focal length away from the lens, what you will see, what you will observe here, here is the Fourier transform. And if you go one more focal length, then you observe the second Fourier transform, or Fourier transform of the Fourier transform. Second Fourier transform is found here. And the second Fourier transform is what we have here. This is the first Fourier transform, and it's here. And then it's this is the second Fourier transform. And the second Fourier transform is the same signal, but flipped around, okay? And they say that it is imaginary. From optical physics, you may see that it is folded and real, and it is folded and imaginary, and things like that. That imaginary thing comes from the fact that it may be on the Fourier axis, on the frequency axis, or on the time axis. We don't have a time signal in optics, of course, it's a space signal, but the Fourier transform is really happening in optics. And this is what we have. An interesting observation is that since this is the Fourier transform that we see here at the focal point, if you put the curtain on the focal point, what is the thing that you will observe? That observation will correspond to the magnitude of the Fourier transform. For instance, if we don't have this person here, but if we have a sunlight, okay, at very far away, coming to the lens, and this is the focal length. At the focus, what are we going to observe? Have you ever tried this at home with a lens or something like that? You may find a magnifier glass is a good convex shaped lens. With the sunlight, if you can put a piece of paper or a piece of wood or whatever at the focal point, you will notice a bright dot, a point, right? And you can even burn that thing. So what is this point that corresponds to. That point is the Fourier transform of a constant. It's the Fourier transform of 1. A sunlight is parallel coming into the lens, so it's like a space function consisting of a uniform magnitude of 1. And the Fourier transform of 1 is equal to impulse. So that point is indeed a point, it's a dot, and it's an impulse. And we know that the impulse has infinite height. And because of that infinite height, it is so powerful that it can burn the paper or it can burn the wood piece. That's why using a magnifier glass, if you just hold it towards the sun direction and put a piece of paper on the focal length, you will generate the Fourier transform of 1, which is a singularity, which is an impulse, delta of t, and it will burn the paper. It has very high peak value. So that's the Fourier transform that you see. And if you have another shape, that would correspond to the Fourier transform of other shape, but it will still be quite a low pass thing, and it will be a very small in size. It will be a very small thing, but it will not be a dot anymore. That's why you cannot burn using a magnifier glass unless you are holding it towards the sun. All the other things will not burn. It will just give you a shape over there on the piece of paper, but it's not going to be delta. It will be the Fourier transform of something else with finite energy or power. So optics is an implication of this. But of course, you don't have to remember the optics, but you have to remember the duality property. The Fourier transform of something is capital X. The Fourier transform of capital X is again X, related to X in shape. That is the duality property. Where are we going to use it? We can use it in several examples, which would be otherwise extremely difficult, too difficult. For instance, suppose that you are given a signal like this. x1 of t is equal to 2 times sine capital T divided by t. What is the Fourier transform of this thing? And if you try to put this into the formula of the Fourier transform and take the integral, I wish you good luck for that. The thing that you have to understand is that when you look at it, it's a sync signal on the time axis, okay? And sync signal is some signal that I have seen before, but not as a time signal. When I take the Fourier transform of a rectangular box, its Fourier transform was sync. So this actually looks like a Fourier transform. So I start thinking about this, and after a while, I remember something. I understand and remember that what I really have is something like this. It's like a y of j omega, like the Fourier transform of y of t, which I don't know. I will find. It was this, 2 sine capital T1 omega divided by omega. This is a signal that I know because the Fourier transform of, or the inverse Fourier transform of this, or the Fourier transform pair that will generate this Fourier transform is actually a box of y of t, which is 1 within this range from minus t1 to capital T1 to plus capital T1 and 0 else. So if this is y of t, then its Fourier transform will be this capital Y of j omega. So this is actually the signal that I am considering here is actually the time version of that. So what is the Fourier transform of this x1 of t? Capital X1 of j omega, which is the Fourier transform of x1 of t, will therefore be equal to something related from here. It will be equal to 2 pi times y of minus, not t of course, because it's in the Fourier axis, minus j omega, which is 1 no, it's 2 pi times that one. No, so it's not really 1, it's 2 pi. I can write it like that when omega is less than or equal to capital T1 and 0 else. So this is the Fourier transform of the sink. What is it? It's a rectangular box. On the omega axis, on the frequency axis, it's a rectangular box with a magnitude of 2 pi. So I'm drawing x1 of j omega from minus T1 to plus T1. And I'm writing as T1, but T1 is equal to T. So maybe I should correct at the very beginning. X1 of T is equal to 2 sine capital T1 T over T. So this is the Fourier transform that we have. What does it say? It says that the Fourier transform of sink is a rectangle. You have to, of course, fold it around omega, but it will give you the same signal. So this is x1 of minus j omega actually, but it's the same as x of j omega because it's symmetric around the origin. So the Fourier transform of sink is a rectangle. The Fourier transform of rectangle is a sink. This is the utilization of the duality property. Whenever you see a signal in time domain that looks like a Fourier transform that you have seen before, please apply the duality property. Because if it is in the Fourier time domain, but looks like the Fourier domain of something, the time domain corresponding to that will be the Fourier transform of your new signal. Okay, they are always appearing in couples. For example, we know that, we know it. The Fourier transform of a cosine is 2 impulses, okay, in the Fourier domain, in the frequency domain. So what is the Fourier transform of 2 impulses in time domain? It will be a cosine in the Fourier domain, okay? That is the duality property. And you should better use it that way. Another example I will show you, and this will be the last example for this hour. We will give a break afterwards. The signal I want you to take the Fourier transform is this. 2 over 1 plus t squared. What is the Fourier transform of this? When you look at it, you just look at it. You may want to try the formula, put it inside the integral, try to solve it. In the exam, some of the students just tried to obtain or develop the Fourier series coefficients just by inserting into the formula. That was very difficult. You should use the properties all the time, as long as you can use. So this is a difficult signal to take the Fourier transform. But again, you start thinking about it and you come up with the idea that you know something as the Fourier transform, which is this. This is a signal for which we know the Fourier transform. Have we done the Fourier transform of that one? I'm just checking my notes because this is something that we might have missed. So just I'm asking you, did we do an example of this y of t is equal to e to the minus 2 in magnitude t, this signal's Fourier transform? Did we take the Fourier transform of e to the minus something in magnitude? Maybe I just missed it. I didn't go through this example, perhaps. If we didn't do this example, please write it here so that I will start by doing these examples first in the next hour, and then when we come back to this example, you will it will make more sense. Doğukan says we didn't do that. I agree. I don't recall doing this example yet, but we have to do it. So we will do it, okay? But nonetheless, it doesn't change the utilization of the duality property. If we haven't done it, if we haven't, and Kadir Kemal says yaptık, we did. did we or didn't we? The one that we did with an arctangent, etc., was actually not this one, but it was e to the minus a times t u of t. That's what we did. E to the minus t, e to the minus a t u of t is the example that we did. But we didn't do this e to the minus a times magnitude or absolute value of t yet, as far as I remember. So we will do that again. Anyway, no problem. We will do it in the within the first minutes of the next hour after this. But again, as I say, it doesn't change our concept. Let's assume that we know it, okay? This is, and it will be given in form of tables. You will see that e to the minus a times magnitude of t will be equal to, will give you, sorry, the Fourier transform, which is in this way of putting into the formula. So if this time signal y of t gives you this y of j omega, then we can see that the Fourier transform of this capital X1 of j omega will be 2 pi times this thing in the form of j omega, but flipped around. So it will be e to the minus 2 times omega Salihcan says, shouldn't it be e to the minus t? No, it's not e to the minus t, it's e to the minus absolute value of t. We didn't do it, and we're gonna do it, no problem. You will see that. Because there is an omega square term or a t square term in the denominator. They are different things. I will go through those things again. So it will be, this x1 of j omega will be 2 pi times e to the minus 2 in absolute value of minus omega. And absolute value of minus omega is the same as absolute value of omega. So this will be the Fourier transform of this time signal. So where did you find it? We found it from the fact that actually if we start from this as a time signal, we will get this one. So if we start with this as a time signal, we will get this one as the Fourier transform. That is the duality property. So you have to search for a known signal, a signal that you previously know or you have in the tables. Okay, from the table, you look at it and you see that, there it is. It's there. So from there, no matter whether if it's a Fourier transform signal or a time signal, you can consider it as a time signal or a Fourier transform signal and use this duality property to find the opposite domain. Okay. So obviously, it seems like we haven't seen the Fourier transforms of a few examples like the e to the minus a times magnitude of t and things like that. We will do that. We are going to rephrase it from my previous notes, which I seem to have skipped after the break. So it's now 5 minutes to 10 o'clock. So let's start at 10 past 10. Okay, 10:10. Okay, we will meet on 10 past 10. And I'm going to give a break now.